Hello, in this video, we're going to solve two example problems on shear stresses. Problem 1. A shaft in torsion only is to transmit 2500 horsepower at 570 rpm with medium shocks. Its material is EISI 1137 annealed steel. A. What should be the diameter of a solid shaft? B. If the shaft is hollow with outside diameter 2 times its inside diameter, what size is required? And C. Determine the torsional deflection of each for a length of 10. In this problem, we have three requirements. First is we're going to determine the diameter if the shaft is solid. Second is if the shaft is hollow, given the ratio of the outside and inside diameter, what is the size? It refers to the outside and inside diameter. And the third is to solve the torsional deflection of each, referring to the solid and the hollow shaft, given a length of 10 feet. So these are the requirements. So first is we're going to solve for the diameter if it is a solid shaft. So this is the cross section for a solid shaft. And it is required for us to solve for the diameter. Okay. So in solving for the diameter, we're going to use the equation. The shear stress equation that involves the torque, the centroidal polar moment of inertia, and the torque applied. So this is the equation where torque is equal to S sub S, or the shear stress, times the J, or the centroidal polar moment of inertia, and C, or the distance from the neutral axis to the point where the shear stress is desired. So J, here is the centroidal polar moment of inertia. The S sub S is the shearing stress. But this shearing stress that will be solved in this particular expression is the design stress, meaning that it has been already used with the design factor, because we have a shearing stress that is calculated from the yield strength, and it will be discussed as we go on. T is the applied torque, and C is the distance from the neutral axis to the point where the stress is desired. Okay. So in this illustration, for a solid shaft, the C refers to the radius, or the half of the diameter. Alright. So these variables, such as the centroidal polar moment of inertia, may be of something new to you, or you have already encountered this in your strength of materials, but we're going to discuss here on what table shall we look up in order for us to compute the centroidal polar moment of inertia. In table 81, so in the textbook, of the elements, design of machine elements by V.M. Ferris, we're going to see different variables that are dependent on the geometry of a material or a machine element. So there are different equations for moment of inertia, polar moment of inertia, and the section modulus or the polar section modulus that differs on what type or what sizes of the machine element is. So here in this problem, since the geometry of the shaft is circular, then it has corresponding equations for the moment of inertia, the section modulus, and the J or the centroidal polar moment of inertia. So these are the variables that we are interested, especially this centroidal polar moment of inertia. Okay, so the centroidal polar moment of inertia for a solid shaft is J is equal to pi d diameter of the shaft raised to the 4th power over 32. Okay. And the C, which is the distance from the neutral axis to the point where the shearing stress is desired, is, as I've said earlier, is equal to the radius or the half of the diameter. Okay. Now let's go back to the governing equation in order to solve this first requirement. So the torque when involving shearing stress is equal to the shearing stress times the polar moment of inertia over C, or it is also equal to the shearing stress times the capital Z prime. This Z prime is the polar section modulus, and you can find the equation to solve for the polar section modulus in the table 81. But for this particular problem, we're more interested in using this J in order to solve this the requirement. Now we are going to simplify this equation by substituting the corresponding expressions for J and C. Okay, so those expressions in the previous page for J and C will be plugged in to simplify this torque equation. So T is equal to S sub S times the polar moment of inertia is pi d raised to the power of 4 over 32, and our C is equal to the half of the diameter. Okay, so we're going to further simplify this. We have S sub S times pi d raised to the power of 4 32 times d over 2. Okay, so we're going to cancel out one exponent for d here, so it's going to be 3. Now we have torque is equal to shearing stress times pi times d raised to the power of 3 over 16. Okay, now it could also be transformed into an expression for shearing stress, which is equal to S sub S is equal to 16t over pi d cube, where the unit for shearing stress can be in PSI or KSI, which depends on what will be the units to be used in T and the diameter. Okay, so from this we can transform this in order to obtain the expression for the diameter. So the d cube is equal to 16t over pi S sub S, or d is equal to the cube root of 16t over pi S sub S. Okay, so this equation or this expression will be used in order for us to solve the diameter. Now we have two unknowns here, so we still have to compute for the torque, applied torque to the shaft, and the shearing stress or the design stress. Okay, so here as I mentioned earlier, we can't directly substitute the value of the shearing stress here, so we're going to use a design factor. So we're going to look up for tables where given a condition or a type of loading maybe, or what are the factors that could be used in order for us to determine the design factor. Okay, so but first we'll first obtain the S sub S, or the shear or the design stress. Okay, so the given material is AISI C1137, or as mentioned in the problem is simply 1137, but they are basically the same, and specifically the condition is annealed. Okay, so if you while watching this, I recommend you to look up the textbook in the table in the appendix. So AISI 1137 properties can be found in table 88. So while watching this, kindly open to the page for table 88. So in table 88, for this specific condition for AISIC 1137, the ultimate stress, or the ultimate strength rather, is equal to 85 KSI, and the yield strength is 50 KSI. Alright. In designing for torsion, since the shaft is subjected to torsional stress, we're going to determine the design stress based on the yield strength. So among the properties that we have found from table 8 for 1137, we are more interested on this value, this yield strength. So thus this yield strength will be used in determining the design stress. Now we're going to get the equivalent the equivalent yield strength in shear. So this equivalent yield strength in shear is denoted by S sub ys. So this is called the equivalent yield strength in shear, denoted by S sub ys. Alright. So because this yield strength given in the table 88 is mostly applied when the material is subjected to tensile strength. So being subjected to tensile strength is different when it is subjected to shear strength. That's why we are going to solve to compute for the equivalent yield strength in shear. Okay, so how are we going to determine for the S sub ys? Okay, so from table 87, so you're going to look up table 87. So there is a suggested ratio of the equivalent yield strength and the yield strength of a material. So it suggests, table 87, that S sub ys, or the equivalent yield strength, is equal to 0.6 of the yield strength. So we are going to use the suggested expression in obtaining S sub ys. Thus we are going to substitute the value for S sub y. So 0.6 times S sub y is 50. So we have S sub y is equal to 30 KSI. Okay. But this S sub y is not yet the design stress, because in order for us to solve for the design stress, we're going to consider the factors in order for us to obtain a safer design. So what do you call this factor? It is the design factor, or the factor of safety. So for the design stress, S sub d, or the design stress, is equal to S sub ys over the design factor. Okay, so how are we going to determine the design factor? The problem didn't state a value of the design factor, nor recommended one, but it gave us the condition of the shaft. So it is said in the problem that the shaft is subjected to medium shock. Okay, so medium shock, no? Okay. So medium shock is one of the factors in determining the factor of safety. So medium shock is a type of loading. So we can look this up in table 1.1. So this is table 1.1. Okay, so this table, there are 4 types of loading: the dead load, the repeated, or the mild shock, repeated but reversed and gradual, and the shock load. And they have corresponding factor of safety basing on the ultimate strength, yield strength, and also in the last 2 columns there are 2 specific materials. These materials are the cast iron, or the brittle ones, and the timber. But since our material here is steel, so we are more concerned with looking up the value of the design factor in this column. Okay, so it is medium shock, and we're going to assume that the medium shock is one directional and gradual. So our closest estimate for the design factor is 3. Okay, so let's further assume that it is medium one directional application of the loading and also gradual. So our design factor is 3. Now we can now solve for the design stress. Okay, so let's go back to the obtained expression for the design stress. The design stress S sub D is equal to S sub ys over the design factor. So we can now plug in those values. S sub ys is equal to 30 ksi over the design factor is equal to 3, and thus we have the design stress 10 ksi. Okay, so we can now have the S sub s, or the design stress S sub d, is equal to 10 ksi. Okay, so going back to the equation in obtaining the diameter is d is equal to the cube root of 16t over pi S sub s. So now this is already known. So we have just solved the value of this, and next is we're going to solve for the torque. Okay, so torque. So we have the horsepower equation. So the horsepower equation is HP is equal to N times T over 63,000. Okay, so N is the revolution per minute of the shaft. T is the torque. So the unit for N is RPM, T is in inch-pound, and if it is divided in 62,000, then we're going to obtain the unit of power in horsepower. Okay, so T is in inch-pound and the N is in RPM. Okay, so we are given in the problem that the angular velocity of the shaft is 570 RPM, and the applied power, or the applied horsepower, is 2500 HP. Okay, so now we're going to transform the horsepower equation in order for us to get an expression for the torque. So thus, from HP is equal to N sub T over 63,000, we have an expression for torque as 63,000 HP over N. Okay, so now we'll just have to substitute these values and we can now obtain the value for torque. Now torque is equal to 63,000. Our horsepower is 2500 HP, and our angular velocity is 570. So the unit of a torque should be in inch-pound. Okay, so if you're holding a calculator right now, please verify this and enter those values in your calculator, and the answer should be 276,315.79 inch-pound, or if we're going to convert it into inch kips, so just simply have to divide it by 1,000. So 276.32 inch kips. Okay, so the expression for the diameter can now be solved, because we have just solved the torque and previously the design stress. So for the diameter, we will just have to plug in those values. Therefore, the diameter is equal to the cube root of the 16 times the torque. The torque is 276.32 inch kips over pi, and what was our design stress again? So it is 10 ksi, or 10 kips per inches squared. Okay, so kips should be cancelled, and under this cube root equation, so this should be in inch cube, and the final diameter, or simplifying this equation, so we have the diameter of 5.20 inches. Okay, so 5.20 inches is not a standard size. Okay, so if you're going to purchase a shaft of 5.20, so you might not be able to purchase one, since this is non-existent. So the available in the market are the standard sizes. So the nearest standard size for 5.20 is 1/4, or the 5 1/4 inches. So the nearest standard, so we're going to indicate it here. So the nearest standard size is 5 1/4 inches. So thus the size of the shaft, diameter of the shaft in our first requirement, if it is a solid shaft, is 5 1/4 inches. Alright, so that is our first requirement. Now let's go to our second requirement. So our second requirement is we're going to determine the size, which refers to the outside and inside diameter if it is a hollow shaft. And we are given the ratio of the outside diameter and the inside diameter, which is the outside diameter is 2 times the inside diameter. So there's will be our illustration representing the hollow shaft. So we have this, the inside diameter, and our outside diameter is this above. Okay, so essentially the steps in solving the second requirement is the same with the first requirement, only that there involves two sizes for the hollow shaft, and these are the d sub I and d sub O. So since there involves these two dimensions, the equation or the expression for the central dipolar moment of inertia is different with the solid shaft. So going back to table 81, okay, so in table 81 we have you can see there a solid shaft and a hollow shaft. So they have different expressions for J. So hollow shaft for table 81, can you look up table 81? J for the hollow shaft is equal to pi over 32 times quantity d sub O raised to the power of 4 minus d sub I to the 4th power. Okay, so now the expression in obtaining the diameter, the original expression is the same with the solid shaft. Okay, so the equation for the shear stress is S sub S is equal to Tc over J. Okay, so this J, this expression is will be plugged in here, and here is what would be our C, or the distance from the neutral axis to the point where the shear stress is applied. So simply, since the torsional stress is applied to the outside surface of the hollow shaft, thus our C is equal to d sub O over 2. Or since d sub O is equal to 2 times the inside diameter, so we can have C is equal to 2 times d sub I over 2. So C is equal to d sub I. Okay, now let's go back to the equation for the shear stress. So shear stress is sub S equals to T times C over J. So we're going to substitute those expressions in the shear stress equation. So torque times d sub I. So we have just solved the expression for dc, which is d sub I, pi over 32. For J is dO raised to the power 4 minus d sub I raised to the power 4. Okay, so going to substitute d sub I is equal to d sub O is equal to 2 d sub I pi over 32, and 2 di is to the power 4 minus di is to the power 4. Okay, so further we're going to simplify those expressions. Di pi over 32, 16 di4 minus di4. Further, S sub S is equal to TDI times over 5 over 32 times 15 DI raised to the power 4. So going to cancel out the 1 power of DI, and thus we have 3. So we have S sub S is equal to 32 T over 15 pi DI raised to the power of 3. So further, we can now get the expression for DI, which is equal to cube root of 32T over 15 pi times S sub S, or the design stress. Okay. Alright, so we have just solved the torque in our first requirement, which is 276.32 inch kips, and also the S sub S, or the design stress. So simply here in this second requirement, we'll just have to plug in those values to obtain D sub I. So 32 times 276.32 inch kips over 15 pi times our design stress is equal to 10 kips per inch squared. So we're going to cancel kips, and this is going to become inch cube, and thus we have 2.66 inches. Okay, and the DO, or the outside diameter, which is equal to 2 times of the DI, is equal to 5.31 inches. Okay, so we obtained this value for D sub I, but likewise with our previous calculations, we're not going to use these values. So we must use the standard value for the final diameter, D sub I and D sub O, to be declared. Okay, so these are the standard sizes that are typical for a shaft bolt sizes, especially in the imperial system. So 1/4, 5/16, 3/8, 7/16, 7/16, 1/2, 5/8, 3/4, 7/8, and the 1. Okay, so we have computed the D sub I as 2.66 inches. Okay, so 2.66 inches, we're going to look at this 10th decimal place in this value. So 0.66 is between 5/8. If we are going 5/8 is, if this expression decimal is 0.625, and 3/4 is 0.75. So 0.66 is higher than 5/8 but lower than 0.75. And I've mentioned in the previous example problem, the simple stresses, that the optimal standard size to be used is the higher. But there are exceptions. Especially if the computed value is relatively closer to the lower value than it is in the next higher. So for example, this 0.66 is closer to 0.65 than it is to 0.75. So we're going to have a basis before we decide on what standard size to be used. So here we have 2.66. So we're going to set a criteria on the percentage of the difference on the computed value and the nearest standard sizes before we can decide on which one to declare. Okay, so 2.66 minus the closest, or closest is 2.625 or 2.58 over the 2.625 times 100%. So this expression will determine the percent difference of our computed value and the closest standard size. So if you're going to compute this, kindly verify this is 1.35%. So 2.66 is 1.35 closer to this next standard size than it is to 2.75. So the set criteria in practice is if it is lower than 5%, the percent difference of the computed value and the standard size, thus we're going to use that closer standard size if it is below 5%. So here it is our apparent computed percent difference is 1.35%, and this obviously lower than 5%, so we're going to use this value or the standard size of d sub I is equal to 2 and 5/8 inches. Alright, so this is our standard size. Now for our outside diameter, so since outside diameter is equal to 2 times di, so we just simply have to substitute the standard size of d sub I, which is 2 and 5/8 inches, and thus we have do is equal to 5 and 1/4 inches. Alright, so we have just solved the two first requirements, and we're now going to proceed to our third and final requirement, which is the torsional deflection. So torsional deflection is represented, or basically is the angle turned by the shaft from the neutral axis after it is subjected to torsional stress. So torsional deflection for each shaft, so the hollow and the solid shaft, and we are going to decide based on our computation if which one is more rigid. Is it the hollow shaft or the solid shaft being more rigid? So we're going to find out once we solve the torsional deflection of each type of shaft. Okay, now let's first solve for the solid shaft. Okay, so the torsional deflection of when subjected to torsional stress is the pi is equal to the torque times the length of the shaft over the centroidal polar moment of inertia times the modulus of rigidity. And this torsional deflection is in the unit of radians. Okay, so this torque is it could be in inch pound or inch kips. The length, it could be in feet or inches. The centroidal polar moment of inertia can be solved using those expressions that we have just used in requirements A and B, and the modulus of rigidity is a constant for a type of material. So for a iron, it has a corresponding modulus of rigidity, and for steel, it has also its corresponding G. Okay, so we'll assign the torsional deflection for a solid shaft as pi sub theta sub s is equal to dl over gg. Okay, so the torque is already known. So this is 276.32 inch kips. So this is we're going to indicate here as with a check mark. So the length is given. Okay, so in the problem, in the third requirement, it is stated there that the length of the shaft is 10 feet. Okay, and we have an expression for the centroidal polar moment of inertia. Now, what is the modulus of rigidity of a steel? Okay, so you can find the value of the modulus of rigidity G in table 87. So kindly look up in table 87 and the upper part of the table 87, it has it's stated there the G for iron and steel. So for steel, the G is 11.5 times 10 raised to the power of 3 KSI. Okay, so I guess we are now good to go for solving the torsional deflection. So torsional deflection, theta sub s is T sub L T times L times pi d raised to the power 4 over 32 times G. So plugging in values, the torque is 276.32 inch kips. The length is in 10 feet. So for uniformity of units, I'll just have to simply multiply it by 12 so that we can have a unit of inches. So 10 feet is going to become 120 inches. Then in the denominator, pi over 32 is the computed value of the diameter for a solid shaft is 5.25 or 5 and 1/4 inches. So we're going to substitute it here. So 5.25, remember, is the standard size. So that's going to be the value that we're going to use here. So 5.25 inches raised to the power of 4 times the modulus of rigidity, 11.5, times 10 raised to the power of 3 kips per inches squared. So units will be cancelled out here. So the unit for theta sub s should be in radians. Okay, now theta sub s, please put this in your calculator. So while you're watching this, use calculator. Can you verify the value that I have solved? So it is 0.04 radians. Okay, so we're going to convert this unit of angle into degrees. So for theta s of 0.04, and converting to radians to degrees is for a pi radian is equal to 180 degrees. So this is 0.04 radians. So therefore our torsional deflection for a solid shaft is 2.22 degrees. Okay, so that is our one of the requirement of in letter C. So next is we're going to compute the torsional deflection for a hollow shaft. Okay, so hollow shaft, we're going to denote theta sub h as the torsional deflection for hollow shaft. So the same governing equation, TL over JG. But what differs between these two, the hollow and the solid, is that they have different centroidal polar moment of inertia. The centroidal polar moment of inertia, if you remember, is pi over 32 do raised to the power 4 minus di raised to the power of 4. Okay, so we can directly substitute those values. So, but first, for easy to understand simplified equation, we're going to first substitute this expression in the equation for torsional deflection. So pi over 32 4 minus di 4 times g. Okay, so torque is known, the length is given, DO and DI have been computed, and GI is known. Okay, so substituting directly those values, then we have 276.32 inch kips, 120 inches, pi over 32. Okay, the outside diameter is 5.25 is the power of 4 minus 2.625 raised to the power of 4 times the modulus of rigidity is 11.5 times 10 raised to the power of 3 kips per inches squared, and they should have a unit of radians. Okay, using your calculator there, kindly verify this computed value, and this is 0.041 radians, and thus converting it to degrees by multiplying 180 degrees by radians, and we have this theta h is equal to 2.36 degrees. Now we're going to compare the computed values of the torsional deflections. So the torsional deflection for the solid shaft is 2.22 degrees. For the hollow shaft is 2.36 degrees. Okay, so this is the cross section of a shaft subjected to torsional stress, and this angle is the torsional deflection. Okay, what signifies, or what is the indicator that when you compare two specimen of different materials or different geometry, so which and they have different torsional deflection, one is of course one is higher and the other is lower, so which one should be the more rigid? So which one has more strength and thus more rigid? So by logic, the lesser the torsional deflection is, the more rigid the shaft is. Okay, so this means that the material or this particular geometry has more strength to withstand the applied torsional stress. Therefore, since the torsional deflection of the solid shaft is lesser than its counterpart in the hollow shaft, therefore the solid shaft is more rigid. That's it. Alright, so we have just solved problem number 1, where our first requirement is the diameter if the shaft is solid. The second is the diameters, the DO and DI if the shaft is hollow, where we were given the ratio of the outside and inside diameter, with the outside diameter being 2 times the inside diameter. And the third requirement is the torsional deflection. Torsional deflection is the angle of twist of the cross-section of a shaft when it's subjected to torsional stress. And we are also required to compute the torsional deflection of each type of or geometry of the shaft, being the solid and the hollow shaft. And we were also required to have a comparison between the computed torsional strength and determine or judge which one is more rigid. And it is found out that the computed torsional deflection of the solid is lesser than the torsional deflection for hollow, and by logic we can judge that the lesser the torsional deflection of a material is, it is more rigid. Therefore, we concluded that the solid shaft is more rigid than the hollow one. Now let's go to problem number 2. Problem number 2, a steel shaft is transmitting 40 HP at 500 RPM with minor shock. A. What should be its diameter if the deflection is not to exceed 1 degrees in 20D? This refers to the length of the shaft, which is equivalent to 20 times its diameter. B. If the deflection is primary, what kind of steel would be satisfactory? The first requirement of problem number 2 is what should be the diameter if the torsional deflection is not to exceed 1 degree with length of the shaft equal to 20 times the diameter. So we're going to use the equation for the torsional deflection. So the torsional deflection of a shaft subjected to torsional stress is equal to the torque times the length over the centroidal polar moment of inertia times the modulus of rigidity. Okay, so we are going to assume that the shaft is solid. So nothing else is indicated in the problem that it is a hollow shaft, and it is we are only given its diameter. So our closest assumption is that this shaft is solid. Sorry. And then gonna substitute, since we are already familiar with the expression for the centroidal polar moment of inertia. So the torque and the length. So the length is equals to 20 times the diameter of the shaft. And the centroidal polar moment of inertia for a solid shaft is equal to pi times d raised to the power 4 over 32 times over 32. It is the j, and it is multiplied by the modulus of rigidity. Okay. So it is indicated in the problem that the torsional deflection should not exceed 1 degree. So we're going to use this 1 degree here in this equation. So we're going to substitute the 1 degree in the angle in this equation, but we're not going to directly substitute 1 degree, since this equation is has a unit of radians. So we're going to convert first the 1 degree into radians, unit of angle. So 1 degree is pi radian is equal to 180 degrees. So we have pi over 180 radians. Okay, now so further this equation, we have So this will be cancelled, no? This power for the diameter. So this is going to be in cube, and now we have d cube is equal to 640 times the torque over pi. The torsional deflection is what in pi over 180 radians, or you can simply use pi over 180 times g. Okay, so we have this expression for the diameter equal to cube root of 640t over pi times pi over 180 times g. Okay, so do we have a value of the torque? So I believe we are not given a value of the torque. So we're going to solve first this value from the horsepower equation. So from the horsepower equation, T is equal to 63,000 HP over N. Okay. We are given that the transmitted power is equal to 40 HP and the RPM is 500. So we can just directly substitute those values in order to obtain the torque. 63,000 times 40 over 500. So this torque should be in unit of inch-pound. Okay, so torque is, kindly verify using your calculator, 5040 inch-pound, or in inch kips, this is 5.04 inch kips. Okay, so we can now plug in the remaining values into the expression for the diameter. So we can now solve for the diameter. 640 times the torque is 5.04 inch kips. Pi times pi over 180. The modulus of rigidity is 11.3 times 10 to the power of 3 kips per inch squared. Okay, so we should have a final value when this is evaluated as in inches. So this diameter is equal to 1.73 inches, or let's say diameter is equal to 1 3/4 inches. Okay, so this is our first requirement. Now, the second requirement is we are required to select a steel. Select a steel that satisfies the conditions in the problem. We are given the type of loading, the limit for the torsional deflection. So we're going to select what is the material to be used with those conditions and the type of shaft that is going to be used. Okay, so selection of steel. Okay, so in this requirement, we're going to select a steel with the yield strength, the S sub y, which is approximately equal to the computed value, and which is based on the several factors. Okay, so in prior to selecting the material, we should solve the SY. Okay, no. So and this SY is our prerequisite in order for us to locate or look up for a material which has the closest value of this SY in the tables of engineering materials. Okay, it could be table 88, table 88, or table 87. Okay, but first let's solve for the design stress. Okay, so first is the design stress. For shaft subjected to torsional stress is equal to 16T over pi d cube. Okay, so we can directly substitute those values since we already have a value of the torque, which is 5.04 inch kips, and the diameter, and we have just solved this in the first requirement, which is equal to 1 3/4 inches. So we can now directly obtain the design stress. Okay, so design stress is equal to 16 times 5.04 inch kips over pi. Our diameter is 1 3/4 inches or 1.75 inches cube. So we should have a unit of the design stress in KSI. So kindly verify using a calculator. So we should have a design stress of 4.79 KSI. Okay, so we have 4.79 KSI of design stress. Okay, so how are we going to solve for the yield strength? So in the first problem, we are given a material, and the material we obtain the properties in the tables. For example, if it was located in table 87, then we obtain the S sub y. So in S sub y, we compute the equivalent shearing stress in or the equivalent yield strength in shear, or it is denoted as S sub ys, and there is a suggested ratio of the S sub ys and the S sub y. So we used that ratio, and thus we have obtained the S sub ys. So in S sub ys is where we applied the design factor in order for us to obtain the design stress. So that process is going to be reversed here in this requirement. So in the part, or in the stage that where we like to obtain the yield strength, so we must first compute the equivalent yield strength. So how are we going to obtain the equivalent yield strength in shear, or the S sub ys? So this design stress is expressed as S sub ys over n. Okay, so this is what we refer to as the equivalent yield strength in shear, and thus S sub ys is equal to the design stress times the design factor. So we have a value for S sub S. This is 4.729, but we don't have the value of the design factor. So what is this design factor? Okay, so in the problem, we are given, or it is given that the type of loading is mild loading. So in the table 1.1, as what we've used in the problem number 1, we have a design factor of 3. So this is for mild loading, and it is repeated but not reversed type of loading. So this is we're going to use this. So simply the S sub y s is equal to 4.79 KSI times 3. So we obtain an S sub y s is equal to 14.37 KSI. Okay, so this is not yet the yield strength that we're going to look up in the table, because this is only the equivalent yield strength in shear. So we need to obtain first the yield strength. Okay, so in table 87, it was suggested that the equivalent yield strength is equal to 0.6 of the yield strength. So using this, we can solve for Sy, which is equal to S sub y s over 0.6. Okay, so we have just solved the S sub y s, and thus we have 14.37 KSI over 0.6. So we have S sub y s is equal to 23.95 KSI, or it is approximately equal to 24 KSI. Now we are going to look up in the properties of different engineering materials, particularly steel, which has greater than or equal to 24 KSI of yield strength. We have various tables in the appendix of our reference textbook. So two of these tables showing the properties of steel are the table 87 and table 88. So using these tables, we're going to look up, or we're going to look for steel which has a yield strength of equal or greater than 24 KSI. And if we are going to find values greater than 24 KSI, so we're going to use the closest one. Alright, so here we have several candidates here. So we're going to look up at this table, which is the tensile yield strength. S sub y 55 is the closest, 55 KSI. Okay, 55, 48, 42. So which is closer to 24. So the closest here in table 87 is this. C1020. So C1020 has a yield strength of 42 KSI. Okay, so now there's no other closer, lower than 42 but higher than 24. Okay, so there's no else. Okay, let's go to table 88. So table 88 is the same with 87. This also shows other steel and their corresponding properties. So we're going to look at this third column for the subway. Okay. Okay, so these values here are much closer than it is with the table 87. Okay, so we have, which one is lower than 42? Okay, so we have normalized C1015. So which one is closer? Okay, right, we have 35. C1117 normalized. Okay, so this is our closest. So we can now disregard the steel that we have found in table 87. So let's find lower than 35 but higher than 24. 51. No, 51, 55, 93, 55, 61, nothing. No. Oh no. Okay. Alright, so this is the closest one with 24 KSI. So what we have found here is that the closest steel with to the hypothetical steel that we had solved in the second requirement is the C1117, and its condition is normalized. Okay, so therefore we can now use this. So our steel that we're going to select this problem is AISI C1117 normalized steel with S sub y equal to 35 KSI. Okay, so we have just finished solving problem number 2, where in the first requirement we are required to solve for the diameter of the shaft if there is a limit on the torsional deflection, and the limit is 1 degree for a length of 20 times its diameter. So we have just solved that the diameter is 1 3/4 inches. In the second requirement, we're going to select the steel given that the conditions in the problem are applied, and we use the dimension that we have solved in the first requirement. So the process is basically the reverse in when we are going to solve the diameter, because for example, in the first problem, in solving the diameter, it first started with the property of the given steel. So here in this problem, the second requirement of problem number 2, the steel is unknown. But if the steel is known, we're going to obtain the properties, particularly the yield strength of that material. So we're going to use that in solving the equivalent yield strength and shear. Further, the design stress using the design factor. So in this requirement, in problem number 2, it is the reverse of the process when the steel is, or the material is known. So starting from the equation for the design stress, the S sub S is equal to 16T over pi d cube for solid shaft. We obtain the design stress. Further, the design stress, since we are given with the type of loading, we were able to look up for the suggested value of the design factor, and we use that in solving the S sub ys, or the equivalent yield strength in shear. So in the equivalent yield strength in shear, we use the suggested ratio of 0.6 Sy is equal to S sub ys, and thus we were able to get the S sub y, and we computed the S sub y is equal to 24 ksi. So using the two tables showing the properties of different steel, the table 87 and table 88, we looked for a steel that has the closest yield strength to 24 ksi, and here we found that the closest one is the AISI C1117, which a normalized condition, which has an SY of 35 ksi. Okay, so that's all for this video, and for your inquiries, don't hesitate to message me in our group in the messenger, or you can email me or contact me through the different communication channels. And please wait for my for your next learning task, which I'm going to upload in the e-learning. Alright, so thank you very much, and stay safe, and see you in our